Welcome to the Mentored Engineer. Last time we discussed how to get the force of the cylinder, the downward force, and the moment from our free body diagram. And today we're going to look at calculating the stresses and design factors from those items. Alright, let's go to Mathcad and start here. So the first thing I like to do is put in a text box saying what we're going to do. So in this case, we're going to calculate the beam stress. Alright. So the next thing we're going to do is we're going to look at the section properties. We're going to need to know the area moment of inertia. We're going to need to know the distance to the centroid. And we're going to need to know the area. And all those can be found very easily from SolidWorks. So let's go to SolidWorks here. And what I've always liked to do is to make a sketch. Doesn't have to be anything fancy, just go right through the section that I want. So my interesting line is right there. And I am going to go through both of those. And you can see it flipped it around on me for some reason. So I'm going to look at the section right here, and I've got a nice block of the section. It's actually a pretty good section for a lot of things. It's got a I-beam in the center. It's got two plates boxing it in, so it's good in torsion as well. And then the top plate is just a nice member to have on top. A lot of extra bending stress from that plate. It'd be nice if they had another one on the bottom, but it'll work. Alright, so now that we've got this section, I'm going to go to Tools and, where is it? It's way down here. Evaluate. And section properties right there. Now, I have a shortcut if it's the letter R. I've had that for, I don't know, years and years. Alright, so some of the things I want to look at here are the area. That's probably the easiest one. And the distance to the centroid, which is 0.7 inches. So this is the distance where this dot is in comparison to where the part's origin is. Alright. And you can't really see them on this, so we'll just leave that alone. Just believe me when I say that that's it. It'll make more sense in a second. The next thing we have is the moments of inertia. Now right here you have the principal moments of inertia, and I really don't like using that. If the part is not symmetrical in at least one direction, it'll skew the orientation of this coordinate system and kind of give you numbers that you're probably not expecting. It'll give you the highest numbers, but it won't, they may not be in the orientation that you want to use or readily use it. You know, we pick coordinate systems for a reason that they make sense. Alright, so here we're looking for the moment, or the moment of inertia about the x-axis, which is right here. It's 68.6 inches to the fourth. You can see there's two other numbers here that are of interest. The other one is the one about the y-axis, which is the vertical, which we'd expect to see it less than the x-axis. And the interesting thing is the z-axis is always the sum of the y and the x. Alright, so now we've got those numbers. We wrote them down, and we can go over and we're going to make another sketch on the surface. Alright, we're just going to put a dot right there, and we're going to go there to the origin, and we're going to type in 0.7. Now you can set your SolidWorks up to give you more resolution there. Alright, so I've got distance from the centroid up is 2.8, and the distance from the centroid down is 3.7 inches. Alright, so let's write those down. And let's go back to Mathcad and we'll put those in there. So my area equals to 13.3 inches squared. My area moment of inertia is equal to 68.6 inches to the fourth. I'm going to call it C up. That's the distance from the centroid up is 2.8 inches. And my distance down equal 3.7 inches. Okay, so we got our formulas there for that. Now let's look at the stress. And it's going to be the force of the cylinder divided by the area. And this is from what we did in the free body diagram 2 times ago. Times the moment at A times C up divided by I, right? And now the moment of truth that we all get scared about, what is the actual PSI? We find out here it's almost 2600 PSI, so that's not too bad. Let's specify our material strength. And for I-beams, material strength is 50 KSI. Usually that's an A992 beam. So here we're going to also look at the shear stress, which is the force downward times the area. And this number is probably going to be less than 1/10 of the other one, just because the failure mode is, bending and not shear. We're not twisting this thing. We're not really having a short beam and trying to shear it off. All right, so that's what we do expect. So now let's go ahead and use Mohr circle and add these two together. If you haven't watched the video on Mohr circle, I highly recommend that you do that. Now here I'm adding in a plus, but it really could be plus or minus. Mathcad obviously can't handle that because it's not a mathematical equation. You can't decide whether you want to add or subtract. So it's 1/2 the quantity of sigma plus sigma squared plus 4. Where's my plus sign? Plus 4 times the shear stress squared. Alright, and that is going to equal, it should be a little bit higher than the stress we calculated above, at about 26. That's what I would expect. And now we're going to find out what the design factor is. Alright, we got a design factor of 2.68, which seems a little high because that's 50 and that's 26. So let me see. That's interesting. That's SY and not S dot Y. There we go, 1.92. I'll put DF in there for design factor. I like to look for those DFs when I'm coming back through to check stuff. Alright, and our principal stress here is 1/2. And then I like to just come up here and copy this whole thing and paste it right in there. Let me move this down a little bit. Oops, I'm a little bit too high, so there we go. This should be just about half of that, so we know we're in the right ballpark. And since I'm dealing with shear stress, I'm going to put that 577 factor in there. Once again, to find out where that factor comes from, watch the video on Mohr circle. And I'm also a little bit too high there. Okay, so now I got a slightly higher design factor in torsion, which I would expect since my main failure mode is normal stress and not shear stress. Alright, now I need to do that plus or minus thing. So I'm going to come in here and I'm going to copy all this. Alright, and I'm going to get that out. And I'm going to put in a minus sign, paste that back in there. Change that to a down. And I don't need this because it's just a recalculation of something before. Alright, so look at this. I've got a giant safety factor here, design factor, on the stress. Now, why is that? And then the shear stress, it got a little bit worse than it did up here. So why did it do that? And the thing is that, remember, this was plus or minus, and since my stress here is negative, it counteracts. But I always like to have positive stresses here. So when I see this, I'm just going to go ahead and copy and cut that whole thing out of there, paste in some absolute value brackets, and make it positive. Okay, so you can see here that our design factor actually dropped. So a couple final thoughts on this. The design factors aren't exactly where I'd like to see them. If I was designing this from scratch, I'd want to see I'd probably want to go to 2.5 design factor. And the reason for that is, you know, we're designing something new, we can control how everything goes into it. Looking at this design, since it is, you know, an older design, 30 years old, probably had no calculations ever done on it. You know, there's a couple things that we can justify. Having a 1.8 and a 1.9 design factor, pretty much up to the endurance limit of most steels, especially, you know, the softer steels, the 50 KSI and the 36 KSI rated. We got a lot of room to deform those and stretch those before it's ever a problem. Another thing to keep in mind is the 1.8 design factor is in compression, so the material is not going to form a crack. It also doesn't get reverse loaded, so it's not a real problem there. And then the final thing is the cylinder loads it up pretty slowly when you think about it. You know, it's going to clamp it, and then it's going to go into our low flow pump, and it's going to load that cylinder up pretty slowly. So those things help. There's no way to get more load into it than what we have. So they're not bad numbers. We probably just want to add that to something we check, you know, periodically, you know, every week or month. I wouldn't say every time we necessarily use this. So that's our video for today. We thank you for watching, and thank you for choosing the Mentored Engineer. Thank you.